today's mindful moment. You know, we just sort of accept it, right? Time, this constant tick-tock, 1 second after another. And this arrow of time always moving forward, never backward. But what if that's not the whole picture?
Yeah.
What if time isn't actually this rigid, unchangeable thing, this straight line that everyone experiences the same way?
Right.
I mean, especially when you start talking about physics, our whole idea of time has been totally flipped on its head, especially over the last 100 years or so.
Yeah, exactly. I mean, for centuries, we just went with our gut, with our everyday experience of time,
Right.
But then we started digging deeper, really trying to understand how the universe ticks at a fundamental level. And those ideas we had, well, they just didn't hold up. We had to rethink things.
Yeah.
And that's what this whole thing is about, this
Yeah.
exploration. We're going to dive into how the idea of time has changed in physics. We'll start with Newton, with his solid, absolute view of time.
Right.
And then we'll move into Einstein's world with relativity, where things get a little, relative.
A little mind-bending.
Yeah, a little mind-bending. And we'll even push beyond that to the really weird stuff. And I think, if you're curious about the universe, about how things really work down deep, then this is going to be a wild ride, a lot of cool insights, but we'll try to keep it grounded so you don't get totally lost.
Yeah.
And to help guide us through this, we're going to be looking closely at a book by Stephen Hawking, The Universe in a Nutshell. It's brilliant. And what I love about it is it's not afraid to tackle complex ideas, but it does it in a way that you can actually grasp. It's not just equations and jargon,
Right.
And it kind of jumps around a bit, which is perfect for us because we're not going in a straight line here. We're exploring. So we'll be drawing a lot from chapters like A Brief History of Relativity and The Shape of Time. Those lay the groundwork for understanding how our view of time has shifted so dramatically. It's really a journey from a simple, straightforward idea of time to something way more complex, more interconnected.
Okay, so let's start at the beginning. Isaac Newton, the OG. What was his take on time?
Well, over 300 years ago, Newton laid out this really precise mathematical model for time and space in his book, Principia Mathematica. And for him, time was absolute. It was like a separate, unchanging backdrop to everything that happens.
Okay.
Think of it like an infinite railroad track, stretching out forever in both directions. Everything happens on those tracks, but the tracks themselves, they're not affected by anything. Time just keeps ticking along constantly, eternally, the same for everyone, everywhere.
It's kind of a comforting thought in a way, this steady, unchanging time.
Yeah, maybe. But there were some folks who weren't so comfortable with this idea. Philosophers like Immanuel Kant, they were wrestling with some pretty big questions, like if the universe was created, as many believed at the time, why did God wait an infinite amount of time to do it? Why not create it right away?
Yeah, that's a good question.
And on the flip side, if the universe has always existed, well then, shouldn't everything that's going to happen have already happened? Shouldn't we have reached a point where everything is just sort of evened out,
Like everything's the same temperature.
Kinda.
We'd have a boring universe.
Yeah, a bit bleak. So there were these cracks starting to show in Newton's picture. And towards the end of the 19th century, things got even more interesting. Scientists at the time imagined space as being filled with this invisible stuff called ether. It was supposed to be this medium that light waves traveled through, like water for sound waves. And they figured that light would travel at a fixed speed through this ether, and that our movement relative to the ether would affect how we measured the speed of light.
Okay, so it's kind of like if you're swimming in a river,
Yeah,
you're going to go faster if you're swimming with the current.
exactly.
And slower if you're swimming against it.
Exactly. That's the idea. But there was this experiment, the Michelson-Morley experiment in 1887, that threw a major wrench in the works. They were really meticulous, these guys. They compared the speed of light in different directions as the Earth was moving around the sun. They were expecting to see these tiny variations in the speed, because of our movement through the ether.
Right.
But they found nothing. It was like light was always traveling at the same speed, no matter which way they measured it, no matter how the Earth was moving. It was baffling.
So like no matter which way you swim in the river, you're going the same speed.
Exactly. It made no sense if you thought about space filled with this ether. And that's where Einstein comes in.
Okay, the big guy.
Yeah. He saw this puzzle, this seemingly impossible result, and he had this incredible insight. He said, what if the speed of light isn't affected by our motion at all? What if it's a constant, a fundamental law of the universe? So he proposed this idea, this postulate, that the laws of science, and that includes the speed of light, should be the same for all observers who are moving freely, regardless of how they're moving relative to each other. No matter how fast you're going, no matter what direction, the speed of light is the same. It's a constant.
That's a pretty radical idea. So what does that mean for our understanding of time?
Well, it means that our old way of thinking about time as this universal, absolute thing just didn't work anymore. If the speed of light is constant, then something else has to give. And that something is our measurements of time and space. They become relative.
Relative.
Yeah, relative to our motion. So Einstein showed that time isn't universal. It's personal. It depends on how you're moving. If two people are at rest relative to each other, their clocks will tick at the same rate.
Right.
But if they're moving relative to each other, well, their measurements of time will be different. Yeah, and this has actually been tested. They took these incredibly precise atomic clocks, flew them around the world in opposite directions, and when they brought them back together, guess what? The clocks showed slightly different times. It was a tiny difference, but it was there. And it was exactly what Einstein's theory predicted.
Wow.
So the faster you move, the slower time passes for you relative to someone who's standing still. It's wild, right?
Time-blowing.
And this leads to another one of Einstein's big ideas. Space-time.
Okay.
He realized that space and time, they're not separate things. They're woven together, connected, forming this four-dimensional fabric. So it's not just space and it's not just time, it's space-time.
Okay, so they're like mashed together.
Exactly. And everything that happens, every event, it's not just happening in a particular place at a particular time. It's happening at a particular point in this four-dimensional space-time fabric. And that fabric, it can be warped and stretched and curved. By the way, if you're digging this deep dive into mind-bending physics, you might enjoy channels like Mindful Moments on YouTube. They do these AI-powered analyses of audiobooks that break down complex ideas.
That's cool.
Yeah.
Okay, so we've got space-time, this four-dimensional fabric, but where does gravity fit into all of this? Because Newton, he thought of gravity as this force that acts instantaneously across any distance. How does that work with space-time?
Well, that's where Einstein's theory of general relativity comes in. This was developed around 1915, and it completely changed our understanding of gravity. Instead of being a force, gravity, according to general relativity, is the curvature of space-time. It's caused by the stuff in the universe by matter and energy. Massive objects, they warp the fabric of space-time around them.
Okay, so it's like, imagine you have a rubber sheet stretched out and you put a bowling ball in the middle.
Yeah, that's a good analogy.
The bowling ball makes a dip in the sheet.
Right.
And if you roll marbles across the sheet, they'll curve around the bowling ball because of that dip.
Exactly. And it's not because there's some invisible force pulling the marbles towards the bowling ball.
Right.
It's because they're following the curves in the sheet. And it's similar with planets orbiting stars. They're not being pulled by the star's gravity.
Okay.
They're moving along the curves in space-time that are created by the star's mass.
So gravity isn't a pull, it's a curve.
Yeah, that's the idea. And this curve, it affects time as well.
So the curve affects not just space, but time too.
Exactly. In general relativity, space and time are totally intertwined. They can't be separated. You can't curve space without also affecting time. And that means time itself has a shape.
Time has a shape.
Yeah, it's wild, right? The shape of time is determined by the distribution of matter and energy in the universe. So the universe isn't just this passive background, it's an active player in the whole cosmic dance.
Wow. And this brings up some of the biggest questions, doesn't it? The beginning and the end of the universe in time. Newton, with his infinite timeline, he kind of avoided those questions. But what does Einstein's curved space-time tell us about how the universe began and how it might end?
Well, at first, even Einstein himself wasn't too keen on the idea of a universe with a beginning or an end. Most physicists at the time, they preferred the idea of a universe that had always existed and would always exist, an infinite universe.
Right.
But then, some solutions to Einstein's equations started popping up that suggested something different. These solutions hinted at a universe with a beginning, but a lot of people thought, well, those are just special cases. They don't represent the real universe, you know.
Okay.
And then there's this idea of a singularity.
Singularity?
Yeah, it's basically a point of infinite density. All the matter and energy in the universe squeezed into an infinitely small point.
Oh, wow.
And at a singularity, the laws of physics as we know them, they just break down. It's like the edge of reality.
Yeah, that's pretty intense.
And a singularity would represent a boundary to time, like either a beginning or an end. And there was a lot of debate about whether our universe actually had a singularity at its beginning. Back in the 1960s, two Russian scientists, Lifshitz and Kalatnikov, they claimed they had proved that those singularity solutions, the ones that pointed to a beginning, they only worked in very specific, unlikely situations. They thought that a more realistic solution would be one where the universe contracted for a while, then bounced back and started expanding again, avoiding a singularity.
So like an eternal cycle of expansion and contraction.
Yeah, that was the idea.
But Hawking and Penrose, they challenged that idea, right?
They did. Roger Penrose and Stephen Hawking, they took a different approach. Instead of focusing on specific solutions, they looked at the big picture, the overall structure of space-time. And what they showed was that in general relativity, if you have matter with positive energy density, which is basically everything in our universe, then the curvature of space-time will inevitably lead to a point where time has a beginning. And they made similar arguments about black holes, these regions of space-time where gravity is so strong that nothing, not even light, can escape.
Right.
And their work showed that inside a black hole, time would come to an end at a singularity. And this was huge. It won them a prize in 1968, and it directly challenged the long-held belief in an eternal universe.
So we went from Newton's infinite timeline to Einstein's universe with a beginning and maybe an end. That's a pretty big shift.
It is, but there's a catch.
Oh, there's always a catch?
Yeah. General relativity, it's a classical theory. That means it doesn't take into account the weirdness of quantum mechanics, which is the theory that governs the behavior of matter at the smallest scales.
Yeah.
And near a singularity, like the one at the beginning of the universe or the one inside a black hole, things get so small, so dense, that quantum effects can't be ignored. So to really understand what's going on at those points, we need a theory that combines general relativity and quantum mechanics.
A theory of everything.
Yeah, a theory of quantum gravity.
Okay, so let's talk about quantum mechanics for a bit.
Yeah.
How does it change our picture of reality? You mentioned something about probabilities.
Right. So quantum mechanics is this revolutionary theory that came about in the early 20th century. It all started with Planck's discovery of quanta, these tiny packets of energy, and then Einstein's work on the photoelectric effect. And then these other physicists, Heisenberg, Dirac, Schrödinger, they developed quantum mechanics into a full-blown theory. And it's fundamentally different from classical physics. In classical physics, particles like electrons, they have definite positions and velocities.
Right.
But in quantum mechanics, particles are described by these things called wave functions.
Okay.
And wave functions, they don't tell us exactly where a particle is or how fast it's going. They give us probabilities. So instead of saying the electron is here, we say there's a certain probability of finding the electron here and a certain probability of finding it there.
Well, it's not about certainty, but about chances.
Exactly. And this randomness, this uncertainty, it's baked into the fabric of reality at the quantum level. It's not just that we don't know enough. It's that reality itself is probabilistic.
Wow. That's a huge departure from the clockwork universe of Newton.
Yeah.
So how does this probabilistic view of reality affect our understanding of time?
Well, it means that the very beginning of the universe, that moment of the Big Bang, becomes even more mysterious.
Right.
Because at that moment, the entire universe was incredibly tiny and incredibly dense. So quantum effects would have been dominant. And that means the beginning of time, it's not this clean, sharp point like we might imagine.
Okay.
It's blurry, fuzzy, uncertain. And that's where the idea of imaginary time comes in.
Imaginary time. Okay, this is where my brain starts to hurt a little bit.
Yeah, it's a tough one to wrap your head around. But basically, imaginary time is this mathematical trick that physicists use to try and smooth out the wrinkles in our understanding of the universe's beginning.
Wrinkles.
Yeah, the problems that arise when we try to combine general relativity and quantum mechanics. So imaginary time, it's not like the time we experience. It's a different way of thinking about the time dimension, mathematically speaking. It's kind of like instead of time going forward and backward, it goes sideways.
Time going sideways. That's hard to picture.
It is. But the important thing is that the history of the universe in real time is closely related to its history in imaginary time. They're like two sides of the same coin.
Okay.
And there's this really interesting idea called the Hartle-Hawking no-boundary proposal that uses imaginary time. They suggested that the universe in imaginary time is like a closed surface, like the surface of a sphere, but in 4 dimensions.
A 4-dimensional sphere. In imaginary time. I'm definitely lost now.
I know, it's a lot to take in, but think about the Earth's surface for a second. You can travel all the way around the Earth without ever hitting an edge, right?
Right.
It's a closed surface. And think about the South Pole. It's a point on the Earth, but it's not a boundary. There's nothing south of the South Pole. And The Hartle-Hawking proposal says that the universe in imaginary time is similar. It has no boundary, there's no edge, no beginning point. It's just this self-contained four-dimensional sphere.
So in imaginary time, there's no Big Bang, no moment of creation.
That's the idea. It suggests that the universe, it didn't pop into existence out of nothing. It just is. It's eternal in a sense, but not eternal in the way we usually think about it, with time stretching out forever in both directions. It's eternal in this different imaginary time sense.
So our universe might not have had a beginning at all.
At least not in the way we usually think about it.
Wow. That's a lot of process.
Yeah.
And what about black holes? We talked about how time ends at a singularity inside a black hole.
Yeah.
But you mentioned this other idea, the holographic principle. What's that all about?
Right. So inside a black hole, space-time is warped so extremely that time, as we experience it, essentially comes to a halt at the singularity. It's like the end of the line for time.
Wow.
But there's this growing idea that information, the stuff that makes up everything in the universe, it might not actually be destroyed inside a black hole.
Okay.
It might be preserved, encoded on the surface of the black hole on its event horizon.
Encoded, like written down.
It's more like the information is represented in the pattern of the event horizon, in the way it vibrates and ripples. And this is where the holographic principle comes in.
Okay.
It's this mind-bending idea that suggests that all the information contained within a volume of space can be encoded on its boundary, kind of like a hologram.
Like a three-dimensional image projected from a two-dimensional surface.
Yeah, kind of like that.
Yeah.
So if we apply this to black holes, it means that all the information about everything that fell into the black hole, it might be stored on its two-dimensional event horizon.
Wow. So even though everything seems to get crushed and destroyed inside a black hole, the information might still be there, just spread out on the surface.
That's the idea. And this, along with other ideas from string theory and other advanced physics frameworks, like these things called p-branes, which are basically higher dimensional objects, they all suggest that our understanding of time and the nature of information itself is far from complete.
It's pretty amazing how much our understanding of time has changed. We started with this simple, intuitive idea of time as a straight line, the same for everyone. But then Einstein came along and showed us that time is relative, it's personal, it's shaped by gravity.
Yeah.
And then quantum mechanics threw another wrench in the works, showing us that time is fuzzy, uncertain at the smallest scales. And now we're talking about imaginary time and the possibility that the universe might not even have had a beginning. It's mind-blowing.
It really is. And I think it's a testament to the power of human curiosity and our drive to understand the universe. We keep asking questions, pushing the boundaries of what we know.
Absolutely. And speaking of pushing boundaries, let's leave our listeners with something to think about. If our perception of time is so deeply connected to the structure of the universe, if time itself can be warped and curved, what other aspects of reality, things we take for granted as fixed and absolute, might actually be more fluid, more interconnected than we currently understand? What other surprises might the universe have in store for us?
It's a great question, one that I think will keep physicists busy for generations to come.
For sure. And if you enjoyed this deep dive into the mysteries of time, be sure to subscribe to the show for more explorations into the fascinating world of physics and cosmology.
Yes, and tell your friends, spread the word.
Exactly. And if you want to delve even deeper into the ideas we've discussed today, check out the show notes for a link to purchase Stephen Hawking's The Universe in a Nutshell. It's an incredible book that will really challenge your thinking.
It will.
And above all, keep questioning, keep exploring, and never stop being curious about the universe and our place within it.
Absolutely. That's the key.
Thanks for listening.
Thanks, everyone.